Thank you. So, Athanas asked to me to present you something elementary enough. It will be really elementary, I think. And my aim will be mainly to convince each of you that this way of seeing hyperbolic geometry actually is very efficient and simple. And in my opinion, at least, much more simple than the way it is usually presented in a lot of books. This is after the book by Yves Lejean and myself, which appeared at Oxford University Press in 2012, which is named Hyperbolic Geometry and Hyperbolic Dynamics and Brownian Motion. Because the idea behind is essentially to be able to perform effective computations in the direction of the dynamics, geodesic flow, and so on. So, I begin with Minkowski space. And some more comment, maybe. What's the deep reason which explains it can be simpler to see hyperbolic geometry in this way? This is because using Minkowski space, I will mainly use simple linear algebra. So performing linear algebra in this vector space will be essentially sufficient to get what one is needed within the realm of hyperbolic geometry. So I begin by introducing this Minkowski space. So it is a space of 1 plus d dimensions. It will be denoted by psi equal psi naught, psi 1 till psi d in R1 plus d. And d will be any integer not smaller than 2. And of course, the essential thing is the pseudonorm, which is psi 0 squared minus the other squared. So you have 1 plus sign and d minus sign. You have a canonical basis. E equal E naught, E1, E d, which will be pseudo-orthonormal. And shows us to be direct. So I fix an orientation saying that the canonical basis of R1 plus d will be direct. So I have relations explaining that it is pseudo-orthonormal. This will be one if A is equal to J equal to naught, or minus 1 if they are equal and not less than 1. A not orthogonal will be identified with RD. This is an identification justified by the fact that minus the pairing here will yield the Euclidean norm on RD when restricted to RD, of course, and also the orthogonal of E0 and E1 will be identified with RD minus 1. It will be convenient. And so, for example, SD minus 1 will be the unit sphere in RD, and so on. A vector will be said to be light-like if only if it will be isotropic and time-like if only if its pseudonorm is positive, time-like, and space-like if only if it is negative. The light cone will be an important feature, is C, the set of vectors such that they are light-like, of course, and the first coordinate is positive. And the solid light cone is C bar, which will be the set of those vectors such that which are non-spacelike, and positively direct also. Of course, this is the convex envelope of the preceding. The following lemma proves to be useful for any psi prime into the solid cone, we have psi prime pseudonorm larger or equal to the product of pseudonorms. That's it. And equality if and only if they are collinear. Another definition. Pseudo orthonormal basis beta given by vectors in this order of Minkowski space such that the first vector which has pseudonorm 1 is future directed is called a Lorentz frame. Future directed, this means that its first coordinate is positive, directed towards the future. Notation, the first projection will be only giving the first vector of the basis of the frame. And this set of frames will be denoted by half f to the d. I take them direct also, not write it direct. I consider only direct frames. The following most important object will be the Lorentz Möbius group, which I denote by PSO1D. Definition. O1D will be the set of isometries, is the set of endomorphism of Minkowski space, which preserve the pseudonorm and PSO1D, the Lorentz Möbius group. I call it with these two names because often, usually in the literature, you find Lorentz group and Möbius group, and actually it is 2 times the same. So I choose this name. And in O1D. So these are matrices of MD plus 1. Size squared matrices of size D plus 1 with real coefficients. Nota bene, you have index 4 between this group and its main subgroup here. The index is 4. It is very easy to understand. You have only to preserve orientation, so index 2, and then the positive direction, another index 2. So it becomes 4. I can write it, of course. Space of D is those, the set of those gamma in O1D, such that gamma preserves the light cone and orientation. Notation. The subgroup of those gamma in PSO1D, which preserve the first canonical base vector, will be identified and is isomorphic to, of course, SO of D, the rotation group. Will be identified with SOD. And of course, if it also preserves the first vector, it will be SO of D minus 1. I identify this lemma. All these isometries are got by the exponential of matrices. PSO1D is the set of exponentials of little so of 1D, where the Lie algebra S little small so 1D is the set of those matrices, square matrices with size D plus 1, of course, such that A xi is not for any psi in R1D. So these are this is not a surprise. This is very similar to what occurs in the case of SOD. These are I can say antisymmetric matrices for this period. I introduce some more notation because some particular matrices will be very significant and important to follow. E, big E, index J, will be the matrix given by that expression. E and this note, E index J, and so on, are the canonical basis vectors of Minkowski space. Again. As a matrix, this is merely something like that. You have a 1 at the G column. This is the column number note. Number 1, here J is equal to 2, and only notes, and 1 here, and zeros, and zeros. So the size is D plus 1, of course. This one is important because it generates the so-called boosts. So-called boosts, or another name for that is hyperbolic screw. Both is more used by physicists. These are only the exponentials of this matrix. Of course, it appears like that. You will have hyperbolic cosine of t times the first coordinate plus Cj hyperbolic sine of t. The other coordinates are unchanged, and the G1 of index G will be this. And the remaining coordinates are unperturbed. This is the first important type of peculiar matrices in the Lie algebra. Second one are merely rotations, infinitesimal rotations. I denote them by E index KL. This will be this K KL minus EL EK, and displayed as a matrix, you will have nodes. Then, for example, here, a unique 1 plus 1, then some minus 1 here. The other entries are all 0. Again, this is a matrix of size D plus 1. This belongs to SO1D, as in the Euclidean case. At this level, it does not change very much. And of course, these matrices generate the rotation proposition. With these two types of matrices, we can already generate the whole Lie algebra. precisely the matrices Ej with matrices E, K, L, G running from 1 to D and K, L distinct also from 1 to D constitute a pseudo-orthonormal basis of the Lie algebra with respect to the killing norm. So I endow the Lie algebra with its killing form. Okay. I precise the meaning K of E prime is a trace of the compose of the adjoint of E and E prime.
Excuse me. What is the signature of the killing form?
I write it right now. I have not the intention to hide that. So, precisely, they are pairwise orthogonal. And you have K of E, J, EJ. And also for different ones, G prime is also not if G is not G prime, and the same for the rotations. And for the square are 2 times d minus 1, and the opposite, exactly the opposite for the square of infinitesimal rotations. So you have the signature. You have d time plus and d minus 1 over 2 minus 1 sines. In particular, you see that K is non-degenerate. Maybe to be very complete, I precise that pad means the endomorphism given by EA. This is merely this one. Only product of matrices, square matrices. And corollary, K is non-degenerate. One says that SO1D is semi-simple. An elementary but important remark is as follows. For on any frame, Lorentz frame, there is a unique gamma in the Lorentz Möbius group mapping the canonical basis to this Lorentz file. Notation. Beta tilde. Hence, I have beta tilde of AG, which is beta J for any J. Now, two particular subgroups of the Lorentz-Conduce group prove to be particularly important. So, next come two remarkable subgroups. Of the Lorentz-Conduce group. I will consider the particular infinitesimal isometries like that. E tilde J will be EJ plus E1J. I am mixing here an infinitesimal boost with an infinitesimal rotation, like that exactly, for G between 2 and D. Of course, belongs to the Lie algebra. As a first remark, they commute. This one are commuting with each other, So, yeah. E tilde D generate a commutative Lie subalgebra I will denote by tau D minus 1 of XO D1D, of course, isomorphic to R to the D minus 1, on which the killing form vanishes, identically vanishes. Now the corresponding isometries are like that. Definition first, for any real R, I denote by theta index R the exponential of R E1. E1 will play a particular role in the story, and this is only merely the matrix hyperbolic cosine of R, hyperbolic sine of R. This is the simplest hyperbolic screw. And once on the diagonal and not everywhere else. These are boosts. Not all, but some of. And little more complicated, the isometries associated to this subalgebra. For any u, I write note u2 till u d in R d minus 1. I recall the identification. This is orthogonal to E naught and E1. So this belongs to R to the d minus 1. Set its square norm, of course, to be minus its square pseudo norm, and it is merely the usual Euclidean norm. And the associated matrix, I display it now. Will be theta plus index u. This is the exponential of the sum of the E tilde j I just raised with coefficients u, j. And it is displayed as 1 plus u squared, this one, over 2, minus u squared over 2, u squared over 2, 1 minus u squared over 2, then u2, ud, here the same, and here also, here same but with minus signs, and then the diagonal of ones and nodes. It is not complicated to get, since we have merely the third power of this matrix vanishes. So in the exponential you have only 3 terms. So it is not complicated, actually. These are the horizontal translations. So-called horizontal translations. These ones, sum of. Nota bene, the set of theta I with R real, and this set of theta plus u, I denote by t index d minus 1, with u running R to the d minus 1, I specified here, are abelian subgroups of the Lorentz Möbius form.
Can you make a picture? How does this theta u act on Minkowski space?
Can
you make a picture of the action of this guy over Minkowski space?
This is I had the intention to specify this not directly yet now, but here I had the intention to draw some pictures. You will have the hyperbolic space like that, and the first ones map, for example, this vector to another one here, and t will be something like the distance here with a sign, and the other one will be along eurocycles. The eurocycles will be the levels of this subgroup. So I will draw some picture, but the eurocycles, we shall get them by intersecting the hyperbolic space with hyperplanes parallel to some direct line of the light cone. And this will be an action within this. An eurocycle will be something like that, more or less looking as a parabole. Okay.
The first part of the picture, or the boost.
Yes. And it will move. They will move along geodesics. So I have the intention to specify this fact. At which time I'm?
10 minutes.
10 minutes. Excellent. So this one, of course, is isomorphic to R to D minus 1. The isomorphism is U maps to theta plus U, of course. More notation. A to the D will be the subgroup generated by the union. Union with this. I put them together. The horizontal these horizontal translations and the boosts I defined just before. And A, because this will be the affine subgroup. Of BSO1D. It is closed, and it's the algebra. Is generated, of course, by E1 and the E tilde I denoted before the collection by tau index D minus 1. And since we have the very simple commutation between E1 and this E tilde J, this is simply again E tilde J for any J. We have dimension of the Lie algebra, I denote it by hat to D, is merely D. I come very soon to the decomposition within this group. Remark, first, one particular important vector. This is a light vector, is preserved. theta plus u. It is preserved by the horizontal translations, and its direction is also preserved by boosts, which acts merely by multiplication by this exponential, real exponential, R. And here for any u in R d minus 1. So you have a particular like eigenvector. Now, the composition, it is actually simple. Proposition. But it is also very easy to prove. These are only some simple computational verifications. So I do not make them on the blackboard. It is simple. Any element of this affine group can be written theta plus x theta t only is product of two of these elements in a unique way. And the commutation relation is very simple too. Theta t, theta plus x is the same as theta plus e to the t, x, theta t. For any x in R d minus 1, t in R. Then, for any rho in the rotation group of index d minus 1, this is important, and for any xt like before, I have the commutation relations. When you are conjugating by this rotation, you only have to perform this rotation on the vector x of R d minus 1, and it commutes with theta t. Of course, with SOD, this is much more complicated. This is another story. So it is important here to realize that this is only SOD minus 1. Of course, commutation relations with respect to SOD are complicated. Notation, one more. To denote the elements of this affine group for any x, y in R d minus 1 and R plus star. So y will be a positive real. I denote, this will be also seen as a complex number z. T z will be t x y, and the definition of that will be in this decomposition theta plus x, but theta logarithm of y. This is why I took it positive, of course. Because in this scale, commutation relations is easily written and more intuitive. So my defined group is a set of TZ with Z like that, and the commutation relation over there can be written again merely like that. These are matrices. This is a product of two matrices, and this is only this matrix. So you see by this form of the product that it is isomorphic to the usual affine group of R to the D minus 1. This is commutation relation is the usual affine group of dilatations and translations in the Euclidean setting. So this is the reason for its name. So maybe it's time to finish.
What is the physical meaning of the preferred spatial direction?
I shall come to it in the next part of the talks, of course. I intend to speak somewhat of that. There is one.
Thank you.